right, now that we know where we want to go, let's look at the actual process of the method of joins. So we're now dealing with the method of joins, and I'm just going to conceptually write down for you what you need to do. So in the very first step, you can see that in the picture on the left, there are no support reactions, but the very first thing you need to actually find your way around the structure is the external support reactions. So first thing is to find external forces, and that translates to support reactions. And I would say find all of them, but in some cases you get away without finding all of them. For a beginner, it's always a good idea to look at all of them first. And now let's think about this, right? So we already talked about the fact that trusses act like cable structures, except that they also can be in compression. And if you think back to 2D cable structures, I'm going to make a side note here. So 2D cables. Remember, as we said before, we had the sum of the forces in X and the sum of the forces in Y that we could use to solve this. And this is similar here. And remember that for the cables, we could only solve for two unknowns at a time. And this is true for the method of joins as well. So let's take a look at the structure here. So if I cut node A, if I release node A or joint A, if I release joint A, then I release 1, 2 member forces. If I cut through node C, I release this one, and I have 2 unknown forces if I have my support reactions. However, if I release node B, then I cut through 1, 2, 3, and I cannot solve that because I have 2 equations with 3 unknowns. Impossible. Same is true here at node D, so I cut through 1, 2, 3. I could not solve this. So my second step is to identify first node. Identify first joint at which 2 and only 2 unknowns need to be identified. So no more than that. Of course, you can have less than 2, but that would very rarely be the case. So now in this third step, after you found that node, you release the node. Third, release that joint or node and draw its free body diagram. So I'll do that conceptually here real quick for node A. In our case, that would look like the following. I have this member, I have this member, and then I also have the support reaction. And the support reaction goes up. So, and I'm going to call this here my free body diagram for node A. Right? And now in step 3A, you do an important assumption. So you assume that all members are in tension. Now, what does that mean? That means that we have member AD down here and AB up here. And if you assume them to be in tension, then it would look as follows. I use purple for that. So you have them to be in tension. And maybe you can already observe that this cannot result in equilibrium because I have a vertical component and a horizontal component due to these. And I also have the horizontal component in AD. And you can already see that ADX and ABX, let me point towards that. So ADX and ABX cannot be in equilibrium if they're both pulling to the right. Or vice versa, if you have a force going up and a force going up, they cannot be in equilibrium. So in fact, in this picture, it's probably the easiest to see that AB must point down. This is a given here, the support reaction. And AB is a variable that I assume to be in tension, which I always do, right? Remember this rule here. I always start with assuming in tension, but then I solve my equations. In fact, that is my next step. But if I solve these equations, then I will find that AB must be negative. So my fourth step is use sum of the forces in X and sum of the forces in Y to solve for all unknowns. And we can do that, like, again, this is only conceptually here, but I'm not going to solve it here. We'll do that in an actual problem in the next slide. But then in my fifth step, I have to use my answers or my solutions from the previous cut and translate results over to the next node. So I'm going to do that conceptually as well. So let's say I calculated AB. Let's take a look at the structure again. So let's say I calculated AB and I already know that I must flip this arrow around. So that means that I know what's going on here at AB, but AB is also acting at this node, so I can translate that result over to node B. Similarly, I know what's going on at AD from this cut, so I can bring that information over to here. And remember what we said earlier about node D, that if we would have cut immediately this node, we would have 1, 2, 3 unknowns, therefore it would be unsolvable. However, once I found AD, I can use that information here at node D, and then I can cut because then I have 1, 2 unknowns left only. Again, something we solve in a problem on the next slide, but for the concept now, we use the results and translate them over to the next node. And then last but not least, the sixth step is use information at next node to solve next node with 2 unknowns at maximum. And so you can work your way through that, and you see that all your following results will rely on your previous results. So it's a method that can quickly lead to issues. However, that is what you can do, and then you kind of repeat everything else, right? So repeat until all member forces are known. And once you're done with that, then your final step, so final step is to draw the result sketch. And the result sketch you have seen above. So this is the result sketch here. This would always be the final step that you take and the final representation of your results, and how to get there numerically we will discuss in an actual hands-on problem with actual numbers, and we will work our entire way through. But for now, we have concluded our entire procedure, where we start and where we need to go. And how do we get there is by following these steps and by using your sum of the forces in X and sum of the forces in Y, and everything in between is just to make our life easier to use these equations and to move on with the knowledge that we created through consecutively cutting our way through the system. And that is the procedure for the method of joints.